Okay, good evening or good morning, depending on your time zone. Okay, today I have the pleasure of introducing Katie Slyman. Katie completed her PhD from the University of North Carolina at Chapel Hill with Chris Jones and did her postdoc at Brown with Bjorn Stansted. She's currently an assistant professor at Boston College. So today she's going to talk about tipping mechanism in a carbon cycle model. Go ahead, Katie.
Okay. Um, Hi guys. This is great. This is my first one that I've been able to attend really in person all semester because I don't really have a seminar at this time, but we're now in finals week, and so there's no seminar today. So thank you all for coming at the end of your semesters. So I'm going to kind of lead you through a little bit of motivation and tipping stuff, and then we'll kind of get into like the heart of the problem. I'm kind of planning to speak for about 45 minutes or so, and please feel free to stop if you have any questions at all. And you guys can just like see my normal screen, right? Like it's like just the PowerPoint presentation. Okay, cool. Okay. Okay, so starting off kind of motivation wise. So tipping big picture is this rapid and often irreversible change in the state of a system. And classically, tipping has been considered in climate subsystems such as Amazon rainforest dieback or permafrost loss. There's been a lot of work recently with like AMOC, collapse. And so this has been like, a really big like wealth of interesting problems. And I do want to just point out that while it has been considered like classically in climate subsystems, they also exist in social systems. For example, when a sufficiently large minority changes the societal norm. And illustrations of such processes would include the disappearance of the gender gap in American higher education in the 70s, or like the rapid increasing number of people in 2013 who signaled their support for same-sex marriage. But in general, like these complex systems are our primary motivation for understanding tipping. And so there are three, I would say, quote unquote, like main tipping mechanisms that are, maybe most studied, which are rate-induced tipping, noise-induced tipping, and bifurcation-induced tipping. And we're going to focus primarily on rate and noise-induced tipping today. And we'll get into it a little bit more formally momentarily. But generally, rate-induced tipping occurs when a parameter changes rapidly enough to cause the system to tip between coexisting attracting states. Noise-induced tipping occurs when there are these random transitions between two attractors of the underlying deterministic system. And bifurcation induced tipping occurs when a parameter, passes a critical level at which a bifurcation takes place, and what was a stable state loses its stability or simply disappears. Now, climate change is a rate-induced tipping problem. It is also a noisy system. And so these two components are true for a lot of relevant climate subsystems, which leads us to, we can have a combination of different types of tipping. And so rate and noise induced is kind of maybe one of the most applicable things of doing kind of in these climate subsystems. Okay, so kind of following the work by Pete Ashman et al., I'm going to lay out some of that framework needed to describe rate-induced tipping. Just kind of like a quick intro, so we're kind of all on the same page, and then we'll kind of keep going from there. So we're going to start with an autonomous differential equation where lambda is a fixed parameter. So think like your dynamical systems or ODEs class, where you have this just like fixed parameter and you look at your fixed points and how they would change. But now instead, we want to consider this lambda changing in time. And so we replace this fixed lambda with this lambda function of RT, and we're specifically assuming a couple things about this function. One, that it stays between two fixed values of lambda of our choosing for all time, and we denote these values lambda minus and lambda plus. And second, we assume that the limit at negative infinity is this lambda minus, and the limit at positive infinity is lambda plus, giving us essentially this gradual transition between lambda minus and lambda plus in time. And now with these conditions, a common function for this lambda is a transformation on a hyperbolic tangent, which is a shape down in the corner, and how quickly we transition is dependent on this size of r, where this r was greater than 0. This is not the only type of transformation that you can use as this lambda. However, it's nice because it's monotone and it's a good shape typically for some of the phenomena that we're interested in terms of kind of like ramping up some value of something in one of these climate subsystems. Now, I want to point out that depending on like the choice of this lambda function, you may or may not get tipping, and we'll talk about conditions for tipping in a few slides. But all of this to say, we now have a non-autonomous system, right, which are in general a little bit more complicated than their autonomous counterparts. And so how do we deal with this? Because as someone in applied dynamics, I'm trying to use like my toolkit from dynamical systems. And so right now we currently, cannot. So we want to convert back to an autonomous system. And the standard approach to numerically investigate rate-induced tipping is to essentially augment the system by introducing a new variable like S equals RT or S equals T and differentiating, which introduces a new equation with some S dot is 1. However, that's still not great because we still can't use like our kind of dynamics toolbox. I wouldn't have fixed points in that system with that more transition numerical change of coordinates. So what we're going to do instead is that Wieczorek, Chun, and Jones developed a systematic approach for compactification that could be used to study rate-induced tipping. So in this process, the invertibility of the time-dependent parameter, which is that lambda function, is used to make a coordinate transform. And then the system is augmented into like an autonomous n+1, kind of the same thing we just had, dimensional extended system. Now, the compactified system is going to contain equilibria, compact invariant sets, all in this extended phase space, such as like the unstable manifolds, allowing us to really use our tools and methods from our dynamical systems toolbox to study this compactified system. Solutions that remain bounded at plus or minus infinity are going to actually become heteroclinic connections in the compactified system. And just overall, in terms of like a big picture perspective, in terms of takeaway, compactification glues the dynamics at infinity onto like a finite phase space. And so that is kind of the big picture takeaway here. So let's look at just a quick example. So here we have a 1D cubic. We have two stable paths, which are denoted in blue, and we have one unstable path, which is in red. And this is when I was saying that we kind of do the numerical approach that does not give us fixed points. That's how it's currently written in terms of the solution up above. And I want to point out before we go a little bit further that the blue and the red lines are tracking the fixed points in the frozen time system. They are not actually solutions of the problem when time is varying. And so I don't have weird intersections of solutions going on or anything. But what we see here is the following. So notice if we initialize kind of on this maybe upper branch of the stable path, when our rate is moving slow enough, as in this first picture, we're able to continually readjust to the fixed point. And you kind of go where you think you would go. If I ran my dynamics forward, I kind of go where I think I would end up. However, when the rate is large enough, as in the second and third pictures, we see that one, we have this transition between this kind of stable upper branch at negative infinity and the stable the unstable branch at positive infinity, or in that last picture, it goes that upper branch to that lower branch. And so when the rate is fast enough, we're no longer able to keep up, and we change where we go, where we're going. And in regards to the compactified system, why it's a little bit nicer is, again, we have these fixed points and these compact invariant sets for the problem. That's a little bit easier to see what's happening in terms of our dynamics toolbox. So here's the compactified system. Now I'm initializing at a fixed point. When my rate is small enough, I go where I think I'm going to this other fixed point at the end of our kind of ramp function. When we hit some critical rate, I have this heteroclinic connection, between my stable fixed point at the start and my unstable fixed point at the end. And when R is bigger than this threshold, we end up at a different stable fixed point. When does tipping actually happen? In one dimension, the criteria for tipping to occur is straightforward. If your kind of starting spot is not in the basin of attraction of the fixed point of interest at the end of the ramp, no tipping occurs. So in this first picture, our kind of starting spot is still in the same basin of attraction of the fixed point at the end of the ramp, so no R tipping would occur. Otherwise, as in picture 2, we see that that value truly is in the basin of attraction of Z plus in that picture. And so there would be rate-induced tipping. This is not exactly true in higher dimensions. So if it's in the basin of attraction of the other orbit at the end of the parameter, you do actually always have tipping. So if it lies in that basin of attraction of a different attractor at the end of that ramp function, we will have tipping. However, if it's not in that basin boundary, that does not mean that it won't occur. So it could still occur even if it's not in that basin of attraction. So we don't have this kind of yes-no structure in higher dimensions, but we do still have that yes structure. Also, sorry, my lights go off like every 10 minutes. It's very energy efficient, but I'm sorry if I have to move and shake. Okay. So quickly kind of doing noise-induced tipping stuff. So it seems reasonable, right, to modify a system to include the possibility of random effects disturbing the system, right? So a formal way to write this is to consider now the SDE, where F is going to be the deterministic piece, and W is representative of a Wiener process. And the Wiener process is what's used to describe Brownian motion associated with additive Gaussian white noise. Now, in studying stochastic models, the main investigations include, studying how noise affects the mentioned phenomena on a variety of scales, determining if noise can induce rare transitions. And in regard to rare events, themselves, the main focus has really been on like 3 objects, maybe more specifically, which has been the probability distribution of like escape points on a basin boundary, the actual most probable path from a point or from, a orbit or whatever, and then also the expected time of this escape. So kind of within this rare event, rare transition theory, these like 3 questions have kind of been guiding a lot of that literature. And so here we just have a quick example. We see these kind of 2 different simulations of starting at a fixed point, which is the one upper minimum is where I had them started. And then we're going to let these fluctuations act on. We just saw that red one tip because a fluctuation was large enough to take it out of the upper and into that lower well. And then we see also that the blue particle will also eventually have a fluctuation that pushes it down as well. So this is a 1D system, so it is gradient, so it's really nice in regard to kind of these 1D stochastics and gradient systems. There's a lot of really nice theory that kind of answers those questions I just mentioned. It tells me what is my expected time to tip. If I'm going to tip, what's that path that is going to be my most probable escape path? That is not true in other systems per se. And like really, there's no reason that we would expect higher dimensional systems to be gradient unless they were associated with some like special physical, phenomena. And so we want to kind of like figure out these questions that we can't necessarily answer as nicely because there's not this theory that gives it to us exactly. And so just as a final wrap up, here we have kind of like our tipping schematic of the 3 different types of tipping I kind of mentioned. And so this noise-induced tipping, you kind of think as a fluctuation pushing me out of a well and into a different well. And so you can always think about noise-induced tipping when there's like multiple wells, as you could go either way in theory, but potentially one way is easier to tip to than another due to like that barrier that the noise would have to push it over to. The rate-induced tipping, you can think about as a shifting landscape. And so can I continually readjust to the fixed point, or is it too fast? And so I'm unable to continually readjust and I kind of miss that shift of landscape. And lastly, bifurcation-induced tipping, which we're not spending really any time on. Did we change a parameter so that like essentially my landscape actually changes? Okay, so that's kind of like your quick intro to these like tipping phenomena that we're going to talk about. And now we'll kind of get more into the actual question itself. Okay, so the oceanic carbon cycle or the marine carbon cycle is composed of processes that exchange carbon between various pools within the ocean, atmosphere, Earth's interior, and the seafloor. The ocean absorbs much of the world's carbon dioxide. It's the largest sink of CO2 on the planet. And however this goes, like it doesn't, do it without any type of consequences. So this addition of CO2 causes ocean acidification, meaning the pH levels of the ocean are decreasing. And this kind of causes difficulty for marine species and ecosystems, think like coral reefs, etc., to survive. And so these species will have to either adapt to the changing ocean, or they're going to have to risk extinction. And so understanding the carbon cycle is of vital importance for our society, as the preservation of these ecosystems and organisms are tied to fishing, industrial materials, tourism. So it's like very like really part of our everyday life and society. And so Dan Rothman at MIT, he simplified the carbon cycle to its key processes governed by the chemical reaction equations. And he modeled the ocean as an open nonlinear biogeochemical reactor with the goal to study the way in which the carbon cycle responded to like an external CO2 injection. And so Rothman looked through all of these geological records and observed that over the last 540 million years, the ocean's store of carbon has changed abruptly, then recovered dozens of times in a fashion similar to like a neuron spike. So kind of this big flux and then kind of come back and re-regulated. And this excitation of the carbon cycle occurred most dramatically near the time of 4 of the 5 great mass extinction events of Earth's history. And when we talk about mass extinction events, this means that species are vanishing much faster than they're being replaced. And it's usually defined as about 75% of the world's species being lost on a short period of geological time. But obviously that is a little bit of a different time scale than we're typically used to. So that's something less than like 2 million years or something along those lines. And so what we're going to look at now is Rothman's model of an excitable carbon system and kind of look at where we could kind of play with these tipping. And lastly, before I keep going, so what he found really was that he determined that when the CO2 injection rate, that external rate, crossed a critical threshold value, it led to significant disruptions in the Earth system, including those mass extinction events when sustained for sufficiently long. So he kind of almost approached this problem from like a bifurcation-induced perspective when he kind of saw this parameter pass over a threshold. So here is the actual 2D model of the oceanic carbon cycle, again, by Rothman. And the phase plane that we're looking at is the carbonate concentration C and the dissolved inorganic carbon concentration, which is W. And we're looking at the different kind of sigmoidal functions in here are the burial, buffer, and respiration processes of carbonate. And so we're going to kind of look at a couple of main players. So first, the CX term is found in the respiration function. And the CX term is going to be the parameter that we vary to have different possible dynamics. And I'll show those momentarily. And then the new parameter is our external CO2 injection rate. So those are the 2 parameters that we're going to be kind of focusing on, or you're going to hear me talk about as we go through this presentation. I will say there's some cool things that happen in the system. There's a Hoff bifurcation, there's fun dynamics. So kind of a plug for people who are teaching climate things. I often give them this model and have them explore different stuff where they can find periods or periodic orbits and look for these bifurcations. And so it's like a pretty fun exercise in the classroom as well. But here are the different dynamics for varying that CX, that respiration term that we saw. And so Rothman's work has focused kind of on this case where you just have this stable fixed point. And we can see that the other kind of main behaviors that they said were kind of more realistic for our oceans were the bistable regime in that second column, where you have a stable periodic orbit, a stable fixed point separated by an unstable periodic orbit, and then you also have an unstable fixed point in that stable periodic orbit. So just quickly, again, summarizing Rothman's results before we kind of move on to the next. He found that no matter the rate at which you added carbon dioxide to an already stable system, that carbon cycle in the upper ocean remains stable. In response to modest perturbations, the carbon cycle would go temporarily out of whack and experience a brief period of mild ocean acidification, but it would always return to its original state rather than oscillating into a new equilibrium. When he introduced carbon dioxide at greater rates, he found that once the levels crossed a critical threshold, the carbon cycle reacted with a cascade of positive feedbacks that magnified the original trigger, causing the entire system to spike in the form of like a severe ocean acidification. These excitations were really similar to the behavior of the periodic orbit. So we saw that bigger periodic orbit. That's what these excitations actually kind of limited to for a bit. And the system did eventually return to equilibrium after tens of thousands of years, an indication that despite a violent reaction, the carbon cycle would resume to its steady state. And this pattern matched that geological record. So Rothman kind of found what he had aimed to do, which was to explain that geological record. So again, here we see like you could have some, again, just kind of explain that picture out. We have like a perturbation off that fixed point. We see a little bit of oscillation before returning back. However, if it was a more violent change, we saw it almost behaving like that big periodic orbit. And so now we're going to focus on parameter values in our new work, looking at where we have this bistable regime. And so we're going to have this stable fixed point Z star, an unstable periodic orbit gamma U, and a stable periodic orbit gamma S. If you see those anywhere, those are those notations going forward. So rate-induced tipping in this problem is actually like very straightforward. So this is not like the bulk of what we're going to look at today in this system. But what we're going to do is we're going to let that carbon dioxide injection rate be our parameter shift. That's going to be our time-dependent parameter. That's going to be that capital lambda function, how we described it at the beginning of today's talk. Now we know from the literature that I kind of said earlier that a sufficient condition for rate-induced tipping to occur in 2D is that we need our base state at the beginning of a ramp to be in the basin of attraction of the other stable state, which in this case is our periodic orbit, at that future kind of end of the ramp. And so if we kind of numerically explore this, we can setting our external injection to start at 0 and allowing it to ramp up. We see that this does actually happen. And what we're plotting in this picture is that fixed point at the start of that ramp, and then also the unstable periodic orbit, that gamma U, at different possible endings of the ramp, because that was the separatrix of the basins of attraction. So once I see that kind of jump over that unstable periodic orbit, then I know that I'm going to end up, because I've kind of crossed over that basin boundary. And so we see that the condition can be met. You can prove this out analytically where that crossing always happens. And so we choose one such option to look at the numerical simulation right now. And here I picked for convenience 0.4, just so that the basin boundary was very clearly on the outside, but it does happen at an earlier value. So this is going to ramp our external CO2 injection rate between 0 and 0.4 in time, but we're going to look at how fastly we increase that value. And so for R less than some critical rate, we do endpoint track the stable fixed points as seen in the top row of fixtures. Notice that the first two columns are projected back into the 2D space, but really we have introduced this new parameter, so it's really a 3D system, and you can see that in that third column. However, when we ramp up that external CO2 injection rate, to be fast enough, we're able to essentially jump over that basin boundary and we relax to that stable periodic orbit. And so what we're seeing is if that CO2 injection rate is varied fast enough, the system can tip between the states, but before the actual loss of stability of the fixed point, as we saw kind of earlier in that bifurcation kind of more figure with the CX. And physically what this is implying is that the amounts of carbonate in dissolved inorganic carbon could actually change really drastically in a relatively, short time period, affecting the oceans and their current balances and the current pH levels, which is going to, again, tie to all those kind of large scale effects we started with. So again, this problem was fairly straightforward. You have that criteria met, it worked, it always is gonna, happen for ramps large enough. And so we're gonna now move into the second half, which is a little bit more complicated. So now we're going to go to the more noise-induced perspective. And so kind of big picture is that we want to understand tipping events in low-dimensional dynamical systems with additive noise. That's where it's going to allow this kind of additive noise structure on these dynamics. And so this approach implies that we juggle between 2 points of view within these problems, which are going to be the dynamical systems perspective, as well as that stochastic perspective. Now, Monte Carlo simulations motivate our work. We can see what realizations are doing, and then our goal is to explain what we are seeing kind of from this dynamical systems point of view. Additionally, these numerical simulations can be used for corroboration, visualization, which are really needed in these higher dimensions. And then also kind of from this stochastic perspective, the Friedland-Wenzel theory of large deviations is kind of the guiding principles for all of this work in terms of that stochastic side. Friedland-Wenzel theory is used to derive Euler-Lagrange equations, which can be recast as Hamiltonian systems, which are then used to find the most probable path for tipping between kind of your two places, and also can help you to find your expected time to tip. When you convert to this Hamiltonian system, that system is a system of first order equations. And that means that we can now have a system, or no, we now have a system that we can use our toolbox from dynamical systems on. We want to use geometric dynamical systems methods. Sorry, my whole screen just froze. Sorry. Okay. We can use geometric dynamical systems methods. And so we'll look at fixed points, invariant manifolds, heteroclinic orbits. And now the reason that we look at these invariant manifolds is because from Friedland-Wenzel theory, heteroclinic orbits are your candidates for your most probable escape paths between states. And the heteroclinic orbits arise from these intersections of the unstable manifold of like your base state and the stable manifold of that threshold state that you're trying to get to. Additionally, the unstable manifold has another independent meaning. It's the quasi-potential, if you're in stochastics, is related to the projection of the unstable manifold. So it's all kind of interrelated. And so just kind of listing it out, the most probable path is going to be a curve that minimizes the Friedland-Wenzel functional. And just recapping what I said, it's going to minimize the functional leads to our Euler-Lagrange equations, which we then recast as the Hamiltonian system. And so we go through that process using calculus of variations. So let's now kind of look at our system, and we're going to now do a lot of numerics and some other stuff with it. Just a reminder that this is our original deterministic system. And so now the form it's going to take from the SDE perspective is the following. So now F and G are those deterministic pieces we just talked about. Sigma 1 and sigma 2 are our noise strengths respectively on these state variables. And our goal ultimately, right, is understanding this bistable regime. So we're trying to tip from that stable fixed point to that stable periodic orbit. But really what that means in terms of like the mathematics behind it is I really only, my main goal is to tip between Z and gamma S, but that means I really just have to figure out how I tip to that unstable basin boundary, because then I'll just follow the deterministic system after. Because once I get to that threshold, then I would just follow the deterministic dynamics at zero cost. So looking at this picture, we had set in these simulations, sigma 1 and sigma 2 both to be 5. This feels like quite large maybe to people who have done some additive noise before, but it's just large because of the scale of the system. Putting these noise strengths on the system actually only give about 4% of tipping. Out of like millions of simulations as converged results, it gives about 4%. So very, very low likelihood, small, but not vanishingly small. And so we numerically simulate what we're doing to get a sense of like what we're dealing with. And we see that these trajectories, if we look at this picture, are exiting kind of on one side of the unstable periodic orbit, right? It's kind of on this west side only. We're not seeing really anything like randomly exit other places. And so following the methods from earlier, we convert to this Hamiltonian system. Oh, and sorry, before we do that, sorry, I had this switched. Here is our 4D system. This is going to guide our most probable escape path from that fixed point to the basin boundary. And just like really highlighting that, you know, we weren't crazy in terms of where these trajectories were exiting. Here's a density plot, and this is a converged set of distributions. And you can see it's really, really exiting in one spot on this periodic orbit. Okay, so now we have to simulate our invariant manifolds. Again, my goal is I'm trying to tip from that stable fixed point out of that, right, going on the way it's leaving it, and I want to get to that unstable periodic orbit, because after that I'll follow the deterministic dynamics. So what we're going to do to find the unstable manifold of that stable fixed point is that we're going to begin by initializing points in the local unstable manifold using the unstable directions that come from the linearization and parameterizing it using the unit circle. And ultimately, this gives us a set of points in this subspace. Each of these points, we're going to run forward in time, and the collection of these trajectories is going to actually give us our unstable manifold. Okay, so we've taken these points, we integrated these points forward in time, and these collections actually for this unstable manifold. And I'm going to get to better pictures momentarily. We can also find the stable manifold of the unstable periodic orbit. Again, I'll get to better pictures in a second. How we do this is we're going to discretize the points on that unstable periodic orbit. And then we're going to use kind of like flow-clay theory stuff. We're going to find the monodromy matrix, which is that state transition matrix after one period. And it doesn't really matter that location of that start point. We're going to be able to find ultimately thinking almost like a tangent bundle as we move around, and generating that gives us this stable manifold. Okay, so here are some other pictures of it, a little bit more clearly defined. We'll talk about those different colors on the unstable manifold momentarily. And just a quick shout out to Emmanuel. He does some really nice graphics in the 3D on MATLAB, and so these are from him, these next couple pictures. And so in both pictures, that red is going to be the 2D periodic orbit of that unstable periodic orbit. And just a couple more. Ultimately, again, we're trying to tip from one state to the other. And so when we're doing this, we're thinking about finding the trajectory that lies on both of these manifolds, right? Or maybe multiple of them if they exist. And so we have to find the intersections of these manifolds, and you can kind of see them, especially in the second picture, how the pink and the blue are interacting. And so once we find those intersections, that will be our kind of path from one state to the other. Okay, so actually doing that out, so the resulting data structure of like taking all those points, what we're going to do is actually like think about putting all of the points on those manifolds into two data frames, and we create a ball tree for the stable manifold, which is really just saying we partition that data frame into a set of nested balls, and then we'll query the tree to find its nearest neighbor on the unstable manifold data frame, and then I can return the distance and the actual points, and we sort by that shortest distance. What you have to be careful of, though, is making sure that that closest neighbor search ultimately gives me points that lie on the same trajectory. So you want to make sure that you check the tangency of the two trajectories and verify that like they are actually truly extensions of one another, and that they're not intersecting each other or like meeting weirdly at a cusp. We perform this process by inspection of the integration near the intersection point. And once we see they fall on the same path, we're able to integrate both trajectories back to where they came from, giving us this heteroclinic connection. And just kind of like rewinding back to Friedland-Wenzel stuff, Friedland-Wenzel theory says that the heteroclinic orbits are candidates for the most probable escape path in the small noise limit. I should have maybe harped on that a little bit more. Friedland-Wenzel theory is all theory derived, like made for the small noise limit, the vanishingly small noise case. And you saw when I have like sigma to 5, you know, my noise strengths being larger, I'm still in small noise, but it's not vanishingly small noise. And so we have to kind of see how do these kind of objects behave for us away from this small noise limit. And just a couple other like fun maybe theory things. Notice here that we do have two heteroclinic orbits from these intersections, and that they are cycling trajectories. They're going to cycle closer and closer to that periodic orbit, which is actually what Day proposed back in 1996 for these escape or these heteroclinic orbits between these things. But I will say there's like a slight issue, because what we saw simulation-wise was not cycling behavior. We didn't see any cycling in those like simulations I ran. So now we kind of have to explain what we're actually seeing there. Okay. So we're going to kind of introduce these ideas of the river and subriver that Emmanuel, Blake, Chris, and I did for a more the IBDP system. And so how we're going to kind of start this off is that the heteroclinic orbits are associated with 2 points on that initial points that we use to initialize our unstable manifold. So they correspond to essentially 2 angles from our initialization, these 2 heteroclinic orbits. And these 2 angles divide our kind of initialization into 2 arcs of points. The river will be used to describe the set of trajectories on the unstable manifold that cross our periodic orbit with x values on this arc and kind of leave with minimal rotation. And moreover, the heteroclinic orbits are going to form the banks of these river. Okay, so all of the points that are on this circle still are going to leave and kind of cross over when we look at that 2D projection. The other piece that I've now kind of chopped off from that circle does not leave the set. So here we kind of see these points in action. So here we initialize and run these points forward in both 2D and 3D, and we see all of these trajectories eventually kind of exit, right? They kind of flow out in that 2D projection. All the other ones would have kept kind of circling around on the inside. We are also going to now define the subriver, and this is going to consist of trajectories with Maslov index 0. The Maslov index can be directly related to the number of conjugate points that a trajectory kind of picks up. And so we really only need to find the number of conjugate points a river trajectory has to determine if it is or is not in the subriver. And a conjugate point occurs along a trajectory when the tangent space to the invariant manifold at a point has a degenerate projection into CW space. Okay. And moreover, that really means that a conjugate point occurs when there is a fold in the unstable manifold. And from a calculus of variations perspective, kind of circling back, the second variation would be degenerate in these points. And a conjugate point can be conveniently described in Plucker coordinates. And so really the approach to find these is to form the Plucker coordinates of the two-dimensional subspace in R4. And the Plucker coordinates are a way to assign 6 homogeneous coordinates to planes in R4. And it's all in terms of differential forms. And so we can go ahead and calculate these conjugate points. Here are the conjugate points for our 2 heteroclinic orbits. We see that the one case, oh, hold on. My PowerPoint just quit. 1 second, sorry. This is embarrassing. Sorry, it's rebooting. Okay, can you guys see that again? Okay, cool. Sorry about that. Sorry, I lost my train of thought. We found these conjugate points on here, and that really tells us which heteroclinic would be like our, our stable heteroclinic orbit and our unstable heteroclinic orbit. I'll talk about that in what I mean in a second. But what we're kind of seeing is that in the small noise limit, what this kind of tells us is that heteroclinic with Maslov index 0, which would be that top heteroclinic orbit in that set of pictures, would have been our most probable, path between our fixed point and that unstable periodic orbit. Okay, so that's what this tells us. Again, the conjugate point is when I'm going to kind of cross that horizontal line in that second column of figures. And so we can see exactly where I pick it up for my 2 heteroclinics. Now what I'm going to do is I'm going to do this for every single trajectory I had that was in that river, okay? Because I'm trying to figure out my subriver, which are all the ones with Maslov index 0. So I go ahead and I take my entire river. I go ahead and calculate, do I have Maslov index 0 for these different trajectories up until integrating all the way to the boundary of the periodic orbit. And we see that these ones that are highlighted in red, those are all of the trajectories that continue to have Maslov index 0. So we're going to kind of use this now as our future subset. So just a quick picture kind of on what we're seeing happen. If we go back to our stochastic realizations, again, I kind of already mentioned that we have this converged distribution. So we have like millions of samples. And if we create joint plots of the exit locations on that unstable periodic orbit, we see that they're like crazy concentrated in this one area. And if we overlay that subriver, it actually aligns really, really well. And so it kind of, this subriver is really kind of dictating a lot of where these trajectories are exiting. And so it's discovered that this subset of local minimizers is actually what determines where these noisy trajectories are escaping. We still haven't figured out, though, kind of, you know, an exact most probable path. How do we relate that theory back? And so now to understand why the noisy trajectories actually escape via, you know, a specific area when crossing this periodic orbit, we need to calculate the energy required by a path to escape to a higher order. And so this involves the Onsager-Matchliff functional, which becomes relevant when your noise is not vanishingly small. Essentially, the Onsager-Matchliff functional is like a perturbation of the Friedland-Wenzel functional. And our viewpoint is to use the this functional as a selection mechanism among all the trajectories that we find as those local minimizers of the Friedland-Wenzel functional. Again, that's subriver. And so for this system, it holds that the divergence, you know, is positive. And so the functional is going to actually penalize trajectories that cycle around the periodic orbit. And so since like the heteroclinic orbits are going to keep winding around a neighborhood infinitely many times, that's going to blow up. And so those are not going to be my most probable escape paths here. And so when we add this perturbation to our Friedland-Wenzel functional, essentially the heteroclinic connections cease to be their global minimizer. But the idea is to then use this to figure out which one actually is the most probable escape path for small but non-vanishingly small noise. And so kind of big picture interpretation is that the OM or the Onsager-Matchliff trajectory is going to act as a guide for the exiting trajectories of the stochastic system. And so we can go ahead and calculate this actual energy required and figure out where we have this lowest energy. So the two boundaries are our heteroclinics. And now we're looking at the energies required for all of those subriver kind of minimizers, and we can see exactly where our minimum occurs. And if we put that into our 2D space, we see that it is in the smack dab middle, like almost at that mode of this distribution. So it aligns really, really well. And so kind of a quick little bit of a summary before I go to our final point. For these kind of more noise values away from that small noise limit, the cycling is not evident, and a specific subset of the boundary is chosen through which the primary leakage of the escaping paths occurs. And so this is that OM trajectory term, and it's our most probable escape path for a given level of noise. Again, we have noise set to be 5 in these cases. You would have to play with that to see how that changes for this Onsager-Matchliff functional. I recognize that this is a low dimensional model, but it can still give physical insights. And essentially, like the overall results of everything show that if the CO2 injection rate is fast enough, it can cause your carbonate concentration to transition rapidly. And our current anthropogenic emissions can be kind of an example of this. And for like the noise case that we just wrapped up, you're able to not give an early warning sign, but you are able to kind of start seeing these dramatic changes in the carbonate state of the ocean. I do want to stop there because I've gone a little bit past where I wanted to go for that 45 minutes, and I have to head out in 10, so I'll stop there. But thank you all very much.
Okay, let's thank Katie for this very wonderful talk. Thank you, Katie.
Thank you.
Okay, at this time, does anybody have any questions?
I have a question.
Okay.
Very nice talk. Thank you so much. I have two questions. One is very simple to answer. What was the variable Q, the third dimension in your plots?
Yeah. So think about like when you're changing your when you're recasting things as your Hamiltonian system, right? You have your like kind of two pieces. So Q is your kind of counterpart to RW in that case.
Okay, that was the Q that you plotted.
Yes.
So that was a simple question. More difficult question. This is a 2D model without forcing, right? The only forcing essentially how you force the system is by changing your parameter nu. So would it be possible to do this same project with external forcing? Have you tried that? If so, what did you find?
No. So our initial kind of, we have not done that. So the only kind of stuff we've done, we've looked at that internal kind of rate changing in time. So that's, I mean, technically an external forcing, but on that parameter, you know, it's within the system, it's on that parameter. And then we've done just the additive noise to the system as a whole to allow these kind of random fluctuations, you know, affecting your system. The ultimate goal for this work, where we initially kind of were headed, it was an application for the rate and noise kind of working in junction for one another to see how that changed where the stuff was kind of flowing out. The issue with that, it's just a hard problem because you're kind of, you know, keeping track of all of these, this like periodic orbit kind of shifting in time. It's going to almost like form like a weird tunnel. And so that was kind of our main goal with where we were going to head this and where we're still trying to go with it. So we have not done other stuff. It was kind of like we kind of built this up to kind of see these individual pieces to ultimately put them together, but we have not, Hans, did that. Yeah.
Okay, thank you.
There's some work done with it that Dwan does, where they look at multiplicative noise on this system and kind of approach it more from a more, you know, formal kind of SDE perspective on things. And that's something to also consider in the future is multiplicative, because you could think about it really on that CO2 injection rate, if that's where you want that noise to be, in which case you would have those other kind of functions of C and W touching it. And so it does take it more to a multiplicative noise problem if that's what you were looking for. Sorry, that went above, like beyond what you had asked, but there's some work on that as well.
Okay, thank you.
Does anyone else have any questions? If not, then I have two questions, Katie, very quick. Could you have used another ramp function besides your tanh? Sorry.
Yeah. So why we had chosen the hyperbolic tanh was mostly for like what we thought was kind of realistic for what we're kind of thinking about this CO2 injection when we kind of looked at some data about it and like what else is out there, kind of thinking about like it was kind of low and then it has been ramped up and now we're kind of seemingly at this higher level that we've kind of stayed at as a society. So that's why we had like physically relevant chosen the tanh. Again, the tanh is also nice from the perspective of the invertibility, which is nice for the compactification. However, like you can do all this stuff. You may or may not get tipping, but you can do this stuff with like hyperbolic secants have been used as like ramp functions where you kind of like ramp up and then kind of ramp back down. And so there are other choices. We just picked this one more for physical relevance rather than exploring different ramp functions. But yes, you could definitely use other stuff. It was just this one felt actual physically relevant for the tanh here, as well as, you know, having this nice monotonic quality that is useful for analysis.
Okay, last question. Based on your experience with the ramp rate-induced tipping, is bistability a necessary condition?
Oh, no, like you can also like tip off to infinity.
I see.
Yeah, so like if you have yeah, so you don't have to tip to another fixed point. You could also just like tip out of the system and kind of blow up. You can see that sometimes too. So no, it's not a condition. It's just nice when it's nice from analysis perspective when you're tipping from kind of one object to another object rather than exiting your system.
Okay, so anybody else has any other questions for Katie? If not, then thanks again, Katie, for this beautiful talk. Thank you.
Thank you.